from this interval. How do you define solution? So, solution. Because we claim this is the maximal interval existence of solution, right? But there has to be a solution for this T. So what is the solution? How do we define solution on this T? So you claim this is the interval we can extend distance of solution to this interval.
So T is in any of the i's?
Yeah, if T is in the union, so T has to be in some I, right? Yeah. So if T is in this, that means the T is in the union, right? So that means there exists an I interval from this collection of all intervals. So this I is the collection, is the set of the collection of all intervals. So there exists at least one interval, such that T in this interval here. T is in this interval where on which solution beta T is defined. Because for each interval there is a solution, right? So yeah, for this interval, of course, there is a solution. Because all those intervals are the interval where we have solutions, right? Yeah, so we use this to define our solution. So our solution, what's the notation is this, right? Alpha with this initial condition. So our solution is just to be that solution at T. Yeah, so for any T from this set, we can have a curve evaluate at T. Okay, so you can probably wonder.
I'm sorry. Could you repeat that again? Like you said, for any solution of.
Yeah, for any T.
Right.
From this interval, we can find
A solution.
some intervals. Okay. Yeah, on which there's exists a solution, right? Then we just use that solution to be solution of our problem on this interval. Yeah, we use that solution to be solution. This is the solution on the maximal interval. Yeah, so that means this solution has a value, right? Just use that as a value of this solution on the maximal interval. So you might probably have a question about beta. So whether for this interval, yeah, maybe there's another interval, right? Also include T. The curve is gamma. Yeah, so is that a problem? Now keep in mind that our hypothesis is the same as the hypothesis of existence and uniqueness theorem, right? So yeah, that's not a problem. If your T is in another interval, J, for example, on which gamma is defined, beta gamma will be the same, right? Uniqueness, yeah. So we have uniqueness result. So the hypothesis will guarantee to have uniqueness. So it doesn't really matter. So gamma, beta will take the same value. So this is uniquely defined on this interval. So that means, so if in case you pick, in case you find, you use another interval, let's call it J, from this collection of intervals. With T being a point of that interval on which gamma is a solution. And by the uniqueness, because all the curve by the uniqueness of solution gamma and beta will agree. The same t, so it doesn't really matter which interval curve you pick. Okay, so next we can look at further notations. So here's the definition. So capital X, okay, B is a subset of this. That's the vector field. Okay, from B to N. So the vector field is a time-dependent vector field. Right, there's a time, and so some x variables. You have N dimensional vector as for x. So time, so this x is from this subset of this to the n-dimensional space. So x is a time-dependent vector field. X is called a complete vector field if this maximal interval of existence is R. So if the interval can be as large as this, then this point is called complete. But if it's true for every point in B, because this S is T, right? C is the n-dimensional the x variable. So if it's true for every such point as C, then we say X is complete.
It maps all the points to the real line?
If this is R, then we just say S, C, this point is complete.
Why do you say that?
Because the maximal interval is the entire real number line. The time interval is,
maps to the real
yeah.
line.
So that's the largest possible interval is R, is a real number line, yeah. So then this point, that means you can extend, you can find the integral curve passing this point. It's going to be defined on this interval, on the real number line. Okay, so the point is complete, but if it's true for every point, then we will say the vector field is complete. Yeah, so if this is true for every SC in B, right? Then the vector field is complete, the complete vector field. Also, sometimes we say the point is positive complete. Sometimes we say the point is negative complete. That is if the maximum interval of existence is okay. If positive infinity is a subset of this for this point. Then SC is positive complete. If negative infinity is a subset of the maximum interval of existence, then this point is called negative complete. Yeah, so complete, positive complete, negative complete. If the vector field is complete, then it's complete for every point. You pick.
If neither happens, then it's
It doesn't have to be complete, yeah. But it's possible that some vector field is complete, then you may find other special properties of that vector field.